Today's lecture is really, really important. We're going to try to be starting to wrap up the course. Lecture 29, by the way, our very last lecture will be lecture 35. Lecture 34, we're going to review for exam 3, and lecture 35, we're going to review for the final exam. So as far as new content goes, it's mostly through lecture 33. So we're starting to wrap things up. We're going to take the content of calculus. We're going to pretend like it's a Christmas present, and we're going to be putting it in a box and wrapping it up and putting a bow on it. Okay, we're starting that process today. Some really cool stuff in my mind that we're going to be talking about. Lecture A will continue talking about the mean value theorem and its corollaries. Corollaries are things that follow from theorems that are also important in their own right. We'll get into more detail then about parametric equations and curves. We started talking about that last time, modeling motion. More motion and parametric equations in lecture B. And then we start talking about definite intervals as opposed to indefinite intervals. And something called the fundamental theorem of calculus. That sounds important, huh? FTC, fundamental theorem of calculus. The discovery of that theorem by Newton and Leibniz was really the start of calculus, you might say. The discovery of that fact, okay? That's going to go back to what we talked about the very first lecture, the big picture, the big ideas of calculus. We're coming back to that now. We're wrapping up that present and putting a bow on it, all right? So let's continue talking about, to start with here, the mean value theorem. It is a very important fact. MVT, 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 right? You're chanting for it. You're so excited about the mean value theorem. It's so valuable, most valuable theorem. Well, somebody might argue the fundamental theorem of calculus is more valuable, but you know, it happened to have those initials anyway. So here we go. What's the statement? This is the precise statement. Suppose f is a continuous function defined in a closed interval. Okay, closed interval meaning include the endpoints. It's continuous on that interval and differentiable on the open interval. And I mentioned last time, you might wonder, well, why not just say it's differentiable on the closed interval? Well, it's because you can get away with just assuming differentiability in the open interval. And in fact, probably on Monday, I'll show you a couple quick examples that show you that you can get away with just that. Then, there exists a number c between a and b. C is an element of the open interval from a to b. It's between a and b. That's what this means. This is not a point. This is an interval. You have to look at the context as far as the notation goes. So that f prime of c is f of b minus f of a divided by b minus a. The slope of the tangent line to the graph of f at c equals the slope of the secant line between the extreme points on the graph on this interval. We'll do an example. I'll show you the picture here. Here's our example. F of x equals 1/2 x cubed minus 3x. There's our function. The interval we're going to consider is a is -2, b is 3, but those numbers I picked for a and b are pretty arbitrary. I could have picked other numbers. Though if I did pick other numbers, I'd get a different thing for c. The goal here is just to illustrate the truth of the theorem, not to prove it. Okay? We're going to just see what c happens to be for this example. And you can do some algebra to figure it out. First, go ahead and compute the slope of the secant line between the point on the left and the point on the right. Okay, I'll show you a graph here in a minute. F of 3 minus f of -2 divided by 3 minus -2. That's just a rise over a rest. Plug in the numbers. 3 cubed is, well, did I make a mistake? I don't know if that function's wrong or if I don't know what I typed wrong here. I was feeling so good about everything, and now it looks like a mistake. I was making a mistake just in my head. I was forgetting to subtract 3x. 3 cubed is 27 over 2 is 27 halves, minus 9, okay? Minus 18 halves is 9 halves, okay? I made a mistake just in my mind. I forgot to subtract 3x. Plug in -2. -2 cubed is -8. -8 over 2 is -4. Minus 3 times -2 is minus -6 is really plus 6 is 2. Did I make a mistake there? What do we have here? We have, we're going to double check again. -4 minus -6. -4 plus 6 is 2. Yes, okay. I believe I didn't make a mistake. You can double check that too. 9 halves minus 2 is 5 halves. 2.5. 2.5 divided by 5 is 1/2. That's the slope of the secant. What about the tangent? Well, here's the derivative. Bring down the 3, get a 3 halves, subtract 1 from the exponent, get an x squared, minus the derivative of 3x is minus 3. Set that equal to 1/2, not 0. Right? We only set it equal to 0 when we're trying to solve for critical points. But that's not what we're trying to do here. We're trying to see when does the slope of the tangent equal the slope of the secant. So I'm setting it equal to 1/2 instead of 0. Solve for x. I'll do that quick on the board here. So I'd have to add 3 to both sides. 3 is 6 over 2. 6 over 2 plus 1/2 is 7 over 2. Multiply both sides by 2/3. The 2's cancel, leaving you with 7/3. X or c must be, well, plus or minus square root of 7/3. But we should check, are both of those really in the interval? In this case, they're both about plus or minus 1.53. They both are in the interval. Sometimes they may not both be in the interval. So sometimes you might only choose one of them. But in this case, they both are. Here's the picture. So the blue curve is our cubic. A is -2. This dot is A comma f of A. B is 3. This dot is B comma f of B. That dashed line is a secant line. It's got a slope of 1/2, right there. We're looking for 2 points where the tangent line has the same slope. It's parallel, right there and right there. Those spots look like they're close to 1.5. Indeed, they are close to 1.5, but not exact. Those are the 2 values of c in this example, where the slope of the tangent is the same as the slope of the secant. I did graph the function over a bigger interval. I could have just graphed it between -2 and 3. I'm ignoring the other parts of the graph. Okay? Again, this is not a proof. It's just to help you believe it. Okay? To believe it's true. You can do more examples. You can do infinitely many examples. Like at my blog, infinity is really big. You can just keep doing math forever and ever. Okay? As long as you live forever and ever, and I hope, being with God in heaven, I'll be able to do math forever and ever. And I think it will be. So it'll be great. Here's a more important fact than you might imagine. It's a corollary of the mean value theorem. It's the constant function theorem. We talked about the increasing function theorem last time. Suppose f is continuous on the closed interval and differentiable on the open interval. Same kind of initial hypotheses of the mean value theorem. If we also assume the derivative is always 0, f prime of x equals 0 for all x in this open interval. It's important to say for all x. We're not after critical points here. Then f must be constant. If the slope of the tangent is always 0, the tangent line is always horizontal, the graph must be horizontal itself. And again, I mentioned how this does not apply to things like the floor function, the greatest integer function, functions whose graphs look like this, for example. This theorem does not apply over the entire domain here because the function is not continuous and it's not differentiable over the whole domain. If you restrict your domain to being, say, some subset over where it is continuous and differentiable like there, then the derivative exists and is always 0 over that interval, and that function is constant over that interval. It doesn't apply over bigger intervals. Don't use the theorem over bigger intervals. Here are a couple corollaries of the constant function theorem. Any 2 antiderivatives of the same function over a given interval must differ by a constant. This justifies adding the plus c in our antiderivative problems to say we've got our most general antiderivative. What's the idea of the proof of this? I'm not going to formally prove this. I'm not going to write out sentences. But what's the idea? Suppose you've got 2 functions. Well, let's start with that. Suppose f prime of x equals g prime of x for all x in some interval. I'm not saying whether the interval is closed or open here. I'm kind of just implicitly assuming these functions are continuous and differentiable everywhere. What does that mean, if that's true? That means f and g are both antiderivatives of the same function. Their derivatives are the same. Whatever this function is, you could call it, I don't know, k of x or something. Both f and g are antiderivatives of k. Their derivatives are k. I would like to show that f and g differ by a constant, that if I subtract one from the other, I get a constant. What you do is do a little trick. Let h of x equal f of x minus g of x. What is my goal? My goal is to show this is constant. That means if I can show its derivative is always 0, then it'll be constant. By the constant function. How do you show the derivative this is always 0? Use your assumption. And linearity, the derivative of h is the difference of the derivatives of f and g. All right, that's linearity of the derivative. And I'm assuming these functions are always equal. Use that assumption. This equals 0. Not just at some value of x, but for every value of x in whatever interval we're talking about. For all x in the interval. You can pretend the interval is the entire real number line. You can generalize this to having the interval be the entire real number line. By the constant function theorem, CFT, that means h of x is a constant, c, for all x. But that means f of x minus g of x is c for all x. They differ by a constant. And another way to write that is to say that means f of x equals g of x plus c for all x in the interval. So this justifies saying if we integrate x cubed, we get 1/4 x to the 4th plus c. I know 1/4 x to the 4th is an antiderivative of x cubed, right? Because you can check it. The derivative of 1/4 x to the 4th, you know, is 4/4 x to the 3rd. X to the 3rd, it is an antiderivative. By adding a plus c, I'm writing the most general form of possible antiderivatives. So this constant function theorem justifies this being your general antiderivative. That's a pretty important thing, actually, including in applications. Thinking specifically of differential equations, in fact, for the applications. There's another application to differential equations. I wrote you a proof on the board here. This is not really a proof because I'm not writing sentences, but it's the idea of the proof. Should have written, do the idea of the proof on the board. Here's the other one. Also because of this theorem, you can say that the only solutions, emphasis on the word only, of this differential equation, dy dx equals y, are functions of this form. Y equals c times e to the x for some constant c. There are no other solutions. That's, again, different than what we've talked about before. Before, what we said is these functions are certainly solutions. We can call them phi of x if we like. I didn't do that here. I could put a subscript here if I like. It's a family of functions. No matter what c is, this will solve the differential equation. Why? Because its derivative always equals itself. It's supposed to be a prime there. For all x. That's what it means to solve this differential equation. Find a function whose derivative equals the function. Y is the function. But this thing here is different. It's claiming something different. It's not saying these functions are solutions. It's saying these functions are the only solutions, no others. What's the idea of the proof of that? Come back over here. Over here, we use the constant function theorem for this other fact, and it involved doing a little trick, defining a new function, h, to be f minus g. Show that's constant with the constant function theorem. We have to do a trick here too. And the trick is a trickier trick than this one. But there is a motivation for it. We're trying to show that if y solves this differential equation, then it's this. That equation would be equivalent to saying y over e to the x is constant. Function of x, if you like, y of x, if you prefer writing that. That's technically not the best notation, but people do it. Constant function. If I could show this as a constant function, I'd be done. How do I show that's a constant function? Maybe the constant function theorem again. Show its derivative is always 0. That's the trick. Let's see. H of x. Well, okay. I should say a little bit more. Suppose I'll go ahead and call it phi of x solves the differential equation. So that means phi prime of x equals phi of x for all x. This derivative of this function always equals itself. Let h of x be this fraction here, except I'll use a phi of x instead of a y of x. Let h of x be phi of x divided by e to the x. It is important to note that you're never dividing by 0 here. E to the x is never ever 0. Never ever. Okay? This is defined and differentiable, in fact, and continuous, because differentiable functions are continuous, for all x. Okay, I'm being a little vague here. You know, what's all x? Well, I could assume these things are, this is true for all x, all real values of x. Okay, I'll show it implicitly. We need to take its derivative so we can show it's always 0 and then use the constant function theorem. How do we take its derivative? Tell me. You've done this kind of problem before, like even on exam 2. Quotient rule. Or product and chain rule. Either way. Let's do the quotient rule. Low d high minus high d low over the square of what's below. That can be simplified a little bit. You can factor the e to the x out at the top. And you can cancel it with one of the e to the x's in the bottom. This derivative simplifies to this. That doesn't look like 0, does it? Well, in general, it's not 0. But what about this problem is going to say that is equal to 0? Look a couple lines above. That's true. I'm assuming it's true. Is that legal? Can I assume it's true? Yeah, that's the point, is to assume it's true. I'm assuming I've got a solution of this. And I want to show that solution must be of this form, c to the x. You need to use your assumptions. Otherwise, you're completely missing the point. So, by this fact right here, this is 0 over e to the x, which is 0 for all x. Now apply the constant function theorem. CFT implies h of x is constant for all x, which implies, because of the formula for h of x, phi of x over e to the x is a constant for all x, which implies phi of x equals c times e to the x for all x. Can't emphasize the importance of continuing to emphasize that these things are true for all x. So I started by assuming I got a function that solves the differential equation, and I concluded that that function must have this formula for some c. I'm not saying what c is, I'm just saying it's some c. This is a pretty significant thing, actually. To know this is the general solution of this differential equation, and you can use that. And there are plenty of other differential equations you'd like to know you've got the general solution for. We will still look at some applications of differential equations to come. I did emphasize verbally it's important to know we're not dividing by 0. Just write that as well. E to the x is never 0 for all x. Okay? Oh, dirty little secret. Some engineers think e to the minus infinity is 0. They're wrong. Right? Infinity is not a number. When you write that, you're really talking about a limit. Now, many engineers know that, but they still write it. I mean, I didn't outline the proof, though. I guess I gave a little bit more detail there. Take a breath. All right, now we'll transition back to the parametric equations, curves, and motion. And then we're, for the rest of the lecture, also going to get into definite integrals. We talked about indefinite integrals and antiderivatives. We're working our way toward definite integrals, thinking about areas under graphs. Remember from lecture 1? Areas under graphs was important. Remember that? We had the cars moving and the vats filling with liquid and the bacteria multiplying or bunnies multiplying and making graphs, and I was drawing areas under the graphs. That's where we're headed now, starting today, to wrap up the course. All right, let's start simple. Modeling straight line uniform motion in a plane. A bug walks at a constant speed over the course of 10 seconds from the point 4, -8 to the point -1, 4. And we're going to suppose lengths are in centimeters to try to make this semi-realistic. What's the goal? The goal is to find parametric equations for the path of the bug. And I should say not just the path itself, but also emphasize the actual motion of the bug, not just the path it walks on. It's a little bit more. When you say path, you really mean a little bit more. Not just the curve or the straight line, but the actual nature of the motion. Is it fast or slow? Is it speeding up or slowing down? That's important too, because we're talking about motion. So parametric equations, like I said last time, are equations of the form. Let's give me some more chalk over here. X equals f of t, y equals g of t, where t is called your parameter. It is a variable here. It's typically time. Okay, that's the most common application, though there are other applications. So the goal here to find parametric equations is to find formulas for f and t that would model this motion. There are actually infinitely many possible answers. Really? Yeah, there are. So which one should we pick? How about the most natural one? What do I mean by natural? Any idea? Like starting moment of time, for example? You might as well start time at t equals 0, right? Simplest thing to do. That's what I mean by most natural. And since the bug travels for 10 seconds, end at time t equals 10. So, how do we do this? It's good to make two separate plots first. And then based on the plots, you can figure out the formulas. A plot of x versus time. I guess I don't really need the part of the axes over to the left so much, because I'm starting at t equals 0. And a plot of y versus time. T is going from 0 to 10 in both cases. What's happening to the bug in the xy plane? Xy plane. The bug is starting at 4, -8. Say 4 is here, -8 down here. Starting at that point, traveling along a straight line at a constant speed and ending at the point -1, 4. Right about there. Does the bug go through the origin? Probably not, but maybe somewhat close. I'm guessing maybe like that. So, the motion is from right to left. I'm purposely picking these examples to go from right to left to emphasize that that can happen. I'm going to trace out the graph in the direction of the motion. If you do these things in parametric mode on your calculator, it will trace it in the correct direction. I'm not going to teach you how to use parametric mode. I would highly, highly encourage you over the weekend to learn how. Find videos yourself. Maybe I'll try to find a video using parametric mode in the calculator to graph parametric equations. Very helpful, okay? So think about x and y individually. X starts at 4 when t is 0 and ends at -1 when t is 10. And it should make some intuitive sense that if we're going to travel along a straight line at a constant speed, probably I better try to use a straight line over here too. That would be the simplest thing to try, at least. And look, it's a line you can figure out its slope and its, its vertical intercept. You can figure out the formula pretty easily. X equals f of t, what's the slope? Rise over run. Rise is -5. It's going down, run is 10. -1/2 is the slope. T is the independent variable here. -1/2 t plus 4. That's the vertical intercept. And y starts down at -8 and goes up to +4. -8 up to +4. Connect these dots. That's the straight line. Y equals g of t. What's the slope there? Rise is from, it's a -8. -8 up to 4 is 12. Run is 10. The slope is 6/5. 1.2 if you prefer. 6/5 t minus 8. There we go. Those are the parametric equations. Put them up here. F of t is -1/2 t plus 4. G of t is 6/5 t minus 8. It's probably good to double check that when you plug in t equals 0, you end at the right point here. Plug in t equals 10, excuse me. But when t is 0, you're at 4, negative 8, as we should be. When t is 10, 10 times negative 1/2 is negative 5. Negative 5 plus 4 is negative 1. That's where I want to be, negative 1. And plug in t equals 10 here. 6/5 times 10 is 12. Minus 8 is 4. Which is that 4 right there. Is this really going to be on that line right here? Is it really going to be a straight line? We can confirm that by writing an xy equation of the path. Eliminate the parameter t. How? These equations both have to be true for all t. You could solve, say, this one for t as a function of x, essentially find the inverse function of it and plug it into there, and get y as a function of x. Like this. This implies x minus 4 is negative 1/2 t. Multiply both sides by negative 2. T is negative 2x plus 8. That's really the inverse function of f, but now plug that into g in place of the t. I'll do that over here, so bring the camera over here. Y equals g of negative 2x plus 8 will be how y depends on x, if I've not made a mistake. Looks good, I think. 6/5 times negative 2x plus 8 minus 8. That's a line. Okay, it's certainly along the line. Looks like it's a line. Y equals negative 12/5 x. This is a plus sign, sorry. There. Plus 8/5. In other words, negative 2.4x plus 1.6. The slope of this line should be negative 2.4, negative 12/5, and the intercept here should be 1.6. Looks maybe about right. If I do rise over run here, it's 12 over 5, negative 12 over 5, that's the slope, like we got. And if you try to plug in a point to find the vertical intercept, like plug in this point here into this equation, or b there initially, you're getting that 4 equals negative 12/5 times negative 1 plus b, and that would mean b is 4 minus 12/5. 20/5 minus 12/5 is 8/5, 1.6. Yes, that's right. Let's take our break.